All right, hey, we're gonna continue on with our lecture of chapter 7 and pretty much finish up chapter 7. There's some random sections we don't cover, but we'll cover them before we start 8. All right, so kind of reviewing where we left off for chapter 7. A is we talked about these two different reactions that can occur. One, which was one step where the nucleophile comes in and it forces that X to leave. The other was where the X just leaves. Like if it's super stable, it can take off, no issues, and then a nucleophile will come in and attack. This first one would be a second order reaction because it depends on the concentration of both of these two things. The rate, I should say, depends on the concentration of both of those two things. So if you have less of this, for example, the rate will be slower. If you have more of that, the rate will be faster. And again, that's just because it's a one-step reaction, which requires two reactants. So because of that, a reaction like this, we're going to call it SN2. Now throughout, my N is not subscripted like it should be. I mean, there's a few times where I do it correctly, but I read it so many times that I'm like, forget it. So just SN2, know that it should be subscripted every time. All right, again, this is an SN2 reaction because its rate depends on two different things. We call that bimolecular. Okay, and then we have this reaction where first something leaves, then the nucleophile comes in, so it's a two-step reaction. And that two-step reaction only relies on this first step. This is the rate determining step. And that actually ends up being a rather important concept, but this is the rate determining step. So remember, in the rate determining step, the activation energy is going to be pretty high for that step. And this is only a first order reaction, meaning the rate only depends on this rate determining step, and because there's only one molecule there, that is what's going to determine how fast the reaction occurs. So this is called unimolecular. Bringing back some of your Gen Chem 2 days here. And this we would call an SN1 reaction. Okay, so again, SN2 substitution, it's a substitution reaction or a nucleophilic substitution reaction. S stands for the substitution, N is a nucleophilic, and 2 is the order in which it is. So this has a 2 order and this is a 1 order. Okay, so kind of backwards, right? Because the SN1 has 2 steps, the SN2 only has 1 step, but we got to get it stuck in our brains right now because that's the way it is. Okay, so let's go ahead and remember rate laws a little bit. All right, so the rate law of a reaction helps determine how fast something occurs. So let's say we have some reaction which is like CH3 to Br reacting with it's negative. All right, so our O right here, this thing right here is the nucleophile, and it's going to attack this, causing this Br to take off. Okay, so we get something that looks like this. And then plus our Br negative. All right, so again, this was the nucleophile here, and this is what we would call like our Rx. So in other words, our rate is equal to K times our Rx times our nucleophile concentration there. Okay, so let's expand this out. In fact, I should have written it over here a little better and go through this and make sure we kind of remember kinetics. Okay. Remember, these stand for concentrations, and so essentially when it asks something over here like Rx is tripled, technically you just put like a 3 in there and ask what would happen to the rate. So if the Rx is tripled, but this stays the same, if we did put a 3 in there, what would happen to the rate? Well, it would have to be tripled. Next it says, what happens if both Rx and Nu are tripled? So if we put a 3 there and a 3 there, we have a 3 and a 3. If we pulled those out, right, we'd have K3 Rx, 3 Nu, right? Which would be essentially the same as if we combine those as K times 9 times Rx and Nu. Sorry, I definitely ran out of paper there, but essentially these 3's multiply together and it would go up by 9-fold. It would increase by 9 times. All right, if Rx is halved, and Nu stays the same, then rate must be halved. If Rx is halved and Nu is doubled, then we have a 2 times a 1/2, which 2 times a 1/2 would just cancel and be 1, so it would just stay the same. Okay, so I can see throwing something on here that maybe gives a reaction like this and said, what would happen to this rate if this is tripled and this stays the same? And then you'd kind of have to have a general idea of the rate order of this SN2 reaction. Again, I'm just going to keep reminding you repeatedly that this is SN2, and hopefully that helps. Okay, rate is also affected by the R group. So if it's like straight up a methyl group, so like we just had right here, this RX, and the R happens to be a methyl group, this reaction would occur really quickly. But if you have something that's really hidden in there in a tertiary compound like this, it wouldn't happen as quickly. And that maybe should make some sense, because if you have a nucleophile like this, that's kind of big, it's kind of hard for it to get in there, right? There's not a lot of space. And this, again, we talked about in the last class, this would make kind of a poorer nucleophile in that situation. But it's really hard for it to get up in that space. And because it's difficult for it to get up in space, it would take a lot of energy, and the activation energy would be really high, as opposed to this one down here, which would have a really low activation energy. So if this is my energy diagram, right, this would be low, this would be higher, and again, the activation energy would be this right there, and these would be in the middle. Okay, so I say remember that SN2 is a one-step mechanism. Okay, so everything happens at one time. Let me give you that example. Let's look at this mechanism we just did again. Okay, just kind of flipped around. So here we have our Rx, and these electrons come and hit that carbon and push that bromine off. Okay, so in our energy diagram, we should expect that it just be one hump, right? So here we have our initial R to an X thing. Up here, the O is bonding with the carbon is bonding with the Br, and it's like this one's gonna lose and this one's gonna gain, but we got these dashed lines. And then down here, we have our products. Yay, very straightforward, right? Again, the activation energy is from here to here, and we should keep in mind that if this had been something that was like a tertiary bromine, like if it had like an R and an R here, carbon to a bromine, something like that, and if it had been a bromine attached to a carbon attached to 3 different carbons, then that activation energy would have been much higher, right? It would have been like that, okay? All right, the direction of the attack matters when we're talking about SN1 and SN2 reactions. So I'm just gonna give you some examples, even though you have the answer right here that SN2 only works with a backside attack. So if we had a front side attack, let's talk about what that would look like. So let's say you have some R and it's bonded to, let's put a methyl group on a wedge, hydrogen there and a Br there. And we react it with some kind of nucleophile, whatever that is gonna be. Okay, a front side attack, meaning it's coming in the front. As you can picture, like coming straight in through the front of the page like this. Okay? If that's the case, then it's pretty much a straight up substitution. Or I guess, yeah, I'll just draw it exactly the same as I did in the last one. Okay, cool. So nothing changes. It just kind of pushes this one off and everything else remains the same. But with the backside attack, it comes in from the other direction and that shifts things. Imagine if I don't know, I'm not a Longhorns fan, but if it was like this, right? And the molecule is sitting like this and something comes from this side, it shifts things that way. And let's talk about what that would look like. Again, if you have the R, H to BR, and we have this nucleophile. Now I'm going to draw it over here. So, because it's going to attack the backside. Then, again, it took these two things, which were like this, and it shifted them back this way. What am I doing? Keegan Gold, I don't know. We'd come in, we'd have our R down here. The nucleophile would then attack right here. And those two things which were up there will still be up there, but they just moved out of the way this way. Okay, so when they shifted this way, and then in both of these, by the way, you'd have a BR negative. And both of these, they look relatively the same, but if you took this and you replaced like this nucleophile with a bromine, what you'll see is these two are actually mirror images of each other, right? You got a bromine, then you got the hydrogen here, you got that there, you got that there. What happens when you have mirror images of each other? They're enantiomers, right? So if that bromine and nucleophile if these happen to be the same thing, these two things would be enantiomers of one another. So you're always going to get an inversion of inversion of the configuration at a stereogenic center. So anytime you have some kind of stereogenic center, it's going to completely flip. And you will always have this because it's always going to be a backside attack with the SN2, okay? All right, so we'll have lots of practice with this coming up here in a little bit. Really, I feel like this should have gone at an earlier spot, but let's go over this real quick. I said which compound in each pair which compound here would undergo a faster SN2 reaction. So when you're looking at the rate, you want to look mainly at the fact that that's secondary and that's primary, right? So in SN2, the primary is going to be first because it's less hindered. Okay. All right, let's talk about SN1 because SN1 is very different. So using a similar reaction here, now we have this tertiary bromine and acetate. And in SN1, we get this. But if you remember, it's a two-step process. So what would actually happen here, and what I probably should have drawn here, so I'll do it now, is this. The first step of an SN2 reaction, or excuse me, an SN1 reaction is the leaving group leaves. So this BR is going to take off. Okay? What that leaves us with is a carbocation. So we got this positively charged carbon, and now we can react it with the acetate. And this negative charged thing, this nucleophile can then attack that carbon. And that's why you get the O like this, if that makes sense. So that's how you get this final product right here, plus a BR negative. All right, again, two steps. First step will always be it leaves, and then the nucleophile will come in and attack. All right, because this was the rate order reaction, rate determining step, what am I saying? Rate determining step. Because this is the rate determining step, it's the one that's going to determine the rate. So all we care about is rate equals K R X. All right, where this is the only thing that matters, whereas before with the bimolecular, we were looking at two different things. Okay, so it says, what happens to the rate under the following conditions? So if this is our rate law, if this is tripled, we put a 3 there, nucleus stays the same, this would be tripled. Okay, so again, if we put a 3 right here, that is automatically going to make the rate be tripled. If both Rx and nucleophile are tripled, what happens? Well, nucleophile has no effect whatsoever, right? The rate determining step is this one, and because of that, essentially, if the only thing that's going to be affected is this being tripled, so it would be tripled. Again, this part doesn't matter because it's not included in the rate law. All right, if Rx is halved, we don't care about the nucleophile, then it must be halved. And if Rx is halved and nucleophile is doubled, we don't care about the nucleophile. All we care about is Rx, so it would be halved. All right, you should notice a stark contrast between SN1 and SN2. Remember, in SN2, things wanted to go over here. These were going to be the faster reactions. But in SN1, tertiary is a faster reaction. So the more hindered it is, the faster it is. In fact, I realized I did this kind of thing twice, but let's do it on the next page. Let's talk about it on the next page. Okay. Again, the rate determining step is when that leaving group here leaves. So here you have something bound to Br, and here the bromine's about to leave, and that activation energy is what determines how fast the reaction is going to go. So if it's a really big reaction, really big activation energy, remember it's going to take longer. So let's talk about why this was also faster, because we said, hey, this also went increasing rate for SN1. We also said that we increased the rate as we went this way as well, right? And so the reason for that is stability. This one is more stable. If you have a tertiary carbocation, it's going to be more stable. That's for several reasons, but inductive effects tend to be the biggest one. We talked briefly about inductive effects in exam 1, but R groups, carbon groups, essentially donate some of their electron density. They donate some of their electron density to the carbocation here. So these are all arrows, you can't see them very well, pointed directly at the carbocation because they help stabilize it. And this is more stable. Okay. Because this is more stable, it takes less energy for it to occur. So if I were to draw out activation energies for these, this one would be a really big activation energy. And then you'd get subsequently smaller. And this would be a lower one because it's, again, more stable. So the more stable tertiary thing is going to have a lower activation energy, and that's why this reaction would occur faster. I hope that makes sense. This comes from something called the Hammond postulate. Your book gets really into the details, but I feel like it doesn't need to be overcomplicated. If this is more stable, it should have a lower activation energy, therefore it should be faster. And that's pretty much what the Hammond postulate says. It says that the rate depends on the activation energy, and stability depends on the free energy. So this one would have a lower free energy because it occurs more easily. Okay, so what is formed with SN1 reactions? Great question. Okay, so if with SN2, we talked about it only being a backside attack, right? And you're always going to get the enantiomer. But with SN1, two things occur. So check this out, you guys. Remember the bromine leaves, right? Leaving this carbocation. Well, it's a planar carbocation, meaning once this bromine leaves, it's no longer a stereogenic center. There's not 4 different things on it. So it's all within one plane. So this nucleophile can attack from the back or the front equally, and that's what it does. It can attack from the front, in which case it's going to be sticking out, right? So if it attacks from the front, it should make sense that the nucleophile is sticking out. Remember, wedge means it's sticking out of the plane. Or it can attack from the back, and you have a dash going into the plane, so it can come this way, and that's why you have the dashed nucleophile there. So you're going to get a racemic mixture. If you guys remember racemic mixture, you have an equal amount of chiral stuff. One this way and one that way. Okay, so let's do some examples here. Let's say you have this thing. Okay, so we have a tertiary bromine here, and we're going to react it with water. We will come to know that water is a weak nucleophile, and it would like to do this. Okay, so there are two things that can happen. A, we'll get the front side attack. And first I should probably just say, first of all, step one, that leaving group's going to leave. Let's start with the carbocation in both examples. So you'll have this planar thing, right, with a positive charge there. Okay, so in the first one, let's go ahead and do this. We got a positive charge there. And the first one, the H2O, let's go ahead and do a front side attack. So that methyl group will now be on the wedge, or excuse me, on the dash, and the wedge is going to hold that water. And then you still, of course, have this part. Okay. So I'm trying to save space here. But now, don't forget, you had a neutral nucleophile attacking this thing. So a neutral nucleophile will give you what kind of charge here? Hopefully, remember, it's going to leave a positive charge right there. Okay, so if you have a positive charge there, do you remember what happens? Either you're going to follow up with some more water, grabbing that, or your book now decided to switch sides and decided that bromine is what's going to be grabbing that proton. And again, we talked about it doesn't matter if it's going to be water or the bromine. You get the same products. And you'll have, if we clean this whole thing up, and then plus HBr, which in water would break apart. Okay, or B, we take the same thing. So this was front. This is going to be back. So in this one, the carbocation is going to attack from the backside. That. And we're going to get the same thing, just the wedges and the dashes are going to be switched. So now, because it attacked from the back, we're going to put the H2O on the wedge. In other words, in the back, behind the paper, and the methyl group out front. Once again, the Br negative is going to grab that proton. Oh, and I should have drawn the arrow here for those electrons. And the proton electrons are going to go there. And it will result in this guy's enantiomer. Okay, so I get a 50-50 mixture of both of those things. And hopefully that makes a little bit of sense. All right, with SN1 reactions, so I got a fruit fly. With SN1 reactions, you're usually gonna, we'll learn that we'll usually use weak nucleophiles, which mean neutral nucleophiles. So with SN1, you're gonna get really used to the fact that it's going to be usually up there will usually be a follow-up pulling off a proton. Okay. Okay, so let's summarize things so far. We have the SN1 reaction. This is what we just did. This is a two-step reaction. It produces a racemic mixture. So it's got the R and the S configuration. And then an SN2 reaction favors these primary and methyl stuff. Secondary is kind of the cutoff where you can do both, but tertiary is only going to proceed via SN1, by the way. So with an SN2 reaction, we're talking about a one-step, and this only has backside only. So you'll get inversion of the stereogenic center. So you can either draw kind of the same molecule with the nucleophile in place of the X and then just switch the wedge or the dash, or you can draw a mirror image, whichever you prefer, to show that it's going to be kind of an enantiomer product. All right, so primary, secondary, tertiary, that indicates a lot about whether it's going to be an SN1 or SN2, but there are three other things that we need to look at: the nucleophile, the leaving group, and the solvent. So let's go ahead and start by looking at the nucleophile. Strong nucleophiles, especially in high concentrations, go SN1, or SN2, excuse me. Strong means remember when like a negative charge. And especially if they're smaller. Because remember we talked about those big hindered things, those tend to be weaker nucleophiles. So a strong thing would be a negative charge or smaller nucleophile. Weak nucleophiles tend to favor SN1 by decreasing the rate of any competing SN2 reaction. So that makes sense. So SN1 is going to occur because it drops the rate of SN2 and the likelihood that it will happen. Okay, let's do some examples. So if we have something like, in fact, you know what, I'm going to draw it on paper so I can write it bigger. Oh, my dad's calling, so I got to pause this video, y'all.